Hi everyone, this is my Lab 2 report on projectile motion. In this lab, we will analyze projectile motion in two dimensions using both experimental observations and computational models. The purpose of this lab is to observe real-world projectile motion in two dimensions and analyze its motion using Tracker. We will build a computational model based on Newton's second law and compare predictions using two models with gravity only and gravity plus drag, and compare that with the experimental data. The fundamental principle we will use to understand the motion of an object in projectile motion is Newton's second law. Newton's second law states that the net force is equal to the change in momentum over the change in time, and this can be rearranged into the velocity update formula on the right. In our model, in our computational model without air resistance, we know that there is no force in the x direction. There's only a force in the y direction, which means that the acceleration in x is zero, and so the velocity in the x direction remains constant. On the other hand, we know that gravity acts only in the y direction, which produces a constant downward acceleration in the y. In our second computational model, when we include air resistance, the drag force, we know that the drag force opposes motion, and it applies a net force in both x and y. Thus, this affects motion in both x and y, and the velocity changes in both x and y. Thus, we have a whole nother trajectory. To determine the drag constant B, we applied Newton's second law by saying the net force equals the sum of the gravity and drag force. From this relationship, we solve for the B constant using our experimental data. Here we set the net force equal to ma, which is equal to the force of gravity plus F, the drag force. And for the drag force, we substituted the equation, the formula, negative B times the magnitude of velocity squared times V hat, and we substituted Fg equals to mg. So our procedure was that we threw a paper ball and then we recorded its motion and then we analyzed that motion using Tracker. We then constructed two computation models, one with gravity only and one with the gravity and drag force, and we compared and analyzed differences in three trajectories and we made preceding conclusions. So here is the Tracker video that we analyzed. Here are the initial conditions we used to construct our computational model without the drag force. Here we set the B constant equal to 0 so that the drag force is equal to 0. Here we can see that for a computational model without the drag force, the velocity in the x is not changing because there is no net force in the x direction. However, we can also see that the velocity in the y direction is decreasing at a constant rate, so that means that there is a constant acceleration, and thus a constant net force, which is in this case the force of gravity. Here are the initial conditions for our computational model with the drag force, and here we set the B constant as 0.001, which we found from our previous calculations. Here are the graphs for a computational model with the drag force. Here we can see that the velocity in the y is still decreasing at a constant rate. However, we see a change in the velocity in the x direction, and the velocity doesn't change at a constant rate. Thus, we can say that there is a non-constant acceleration which is caused by the drag force. This is the graph that I created to compare the three computational models. As we can see, the computational model with only gravity is much higher than the experimental model. But when we added the drag force to the gravity, we see that it's much closer to the experimental model. However, there is still some discrepancy due to other errors, as we will explore in the next slide. So in the previous slide, we saw that the trajectory of our computational model was not the exact same as our experimental model. This could be for a few reasons. The first could be calculation errors. It is probable that the calculation of the B constant was too low, which caused the drag force model to be farther than experimental. Other factors may have also influenced this, such as the density changes, object orientation, or other other factors. There may have also been measurement errors such as misalignment of the camera or calibration stick and other small errors in tracking that may have caused the points to shift above this true trajectory. Our model with only gravity is an inaccurate representation of the trajectory and predicts a longer range than the experimental trajectory. Our drag model with drag force fits our experimental model much better, and we can conclude that air resistance has a measurable effect on projectile motion, which provides a more accurate representation of the trajectory. So some additional questions to ask is, did our object achieve terminal velocity? Terminal velocity is when the downward pull of gravity is balanced by air resistance, which results in a zero net force. However, our object did not fall long enough to achieve this balance. Another way to observe this terminal velocity would have been to use a parachute, since a large surface area makes the object slow down and reach a constant velocity. What if another question to ask is what if our object was thrown straight up? Well, since the magnitude of our speed would have been solely in the y direction, if we were to throw it straight up into the air, there would have been a greater initial velocity, indicating a greater flight time. Since the x and y components of the velocity are independent of each other, if we were to apply the same y component of velocity, then the flight times would have been the exact same because gravity would cause it to fall down at the same